My name is Samir Khan and I'm one of the team of product managers here at MapleSoft. My role is to interact with people like you, people interested in our technology, and to help you better understand our tools, products and services. This short webinar is about solving problems more quickly and efficiently with parallel computing and multi-core math in Maple. Before I start, parallel computing sounds very much like a programming concept, a computer science concept. But in actually using Maple, you could already be using parallel mathematical routines without even thinking about it. For example, Maple automatically parallelizes many common math operations. So this is the agenda for today's presentation. I won't go through this in detail, but basically I want to talk about how and why we're embracing parallel computing and multi-core math, and what it means for you, our customers, and what it means for our future plans. I've also prepared a Maple worksheet to demonstrate some of the principles that I'll discuss today. It contains a broad range of automatically multi-threaded functions and examples and benchmarks to test the parallel computation speed of your own computer. I might show you some parts of this worksheet later, just before the end of the webinar, but if you want a copy, contact us for a copy. So, parallel computing is here. It's widely available through tools like Maple and can make a real tangible difference to the way scientists and engineers work. Let me speak about a recent project I was involved in. Oxford Instruments are based in the UK. They research, design and make superconducting magnets. These are used in highly demanding applications like NMR analysis machines. Accordingly, the design of these products must be carefully controlled and precisely engineered. Oxford Instruments use Maple for their design calculations. These worksheets are typically complex and take a long time to compute. Their scientists have to repeat these calculations over and over again with small changes in the design parameters. This often means that they were spending a long time staring at a computer when they could have been doing something a lot more productive instead. They sent their Maple worksheet to us and asked us to find ways of making it quicker and more efficient. We split up the calculations so that they executed in parallel using Maple's local grid computing tools. This typically reduced calculation times on an 8-core laptop by a factor of 3. That's a real tangible time savings, a real productivity benefit. So why go parallel? Well, for many years, processor makers like Intel and AMD increased CPU clock rates. This meant that you could simply make math software like your spreadsheet, Fortran code or Maple run faster simply by buying a faster processor. Around the start of the new millennium, clock speeds leveled off. Well, why was that? As you increase CPU clock speeds, you produce more heat. That heat has to be removed or dissipated. And if you open up your desktop computer, you might find a cooling fan. And clock speeds got so fast that you couldn't remove heat fast enough using air cooling, and providing other methods for cooling, such as water or other liquids, was simply not practical for mass use. In a parallel associated trend, CPU manufacturers were continuously improving architecture so that their chips did more work in a single clock step. But this didn't deliver the speed increases that their customers were demanding. So after the year 2000, as you can see on this chart, chip manufacturers started putting more cores on a CPU to make them more powerful. However, this meant you couldn't make your math software faster just by buying a computer with more cores on the CPU. That software had to be rewritten in order to use the additional CPUs. And that, quite frankly, presents a challenge for companies like MapleSoft. Our customers are solving increasingly more complex problems, and we need to provide tools they need to do their jobs faster and more efficiently than before. So, who are our users? Well, they're typically scientists, mathematicians and engineers, and they use Maple to automate and mechanize repetitive math-based tasks. That could be calculating a symbolic integral or plotting the stress distribution across a bridge. These users aren't computer programmers or software engineers. They may have taken a programming class at university, and they may write scripts for batch processing or automating repetitive tasks. But generally, these users don't care about low-level operations like memory management, thread safety, and race conditions. They need high-level tools that make them productive straight away, out of the box. The challenge that MapleSoft faces is to provide tools that help these users work faster and more productively. And as a company, we've embraced the technological culture of parallel computing. This benefits both novice users and power users. Even minor performance benefits, when compounded, make a real difference to the user experience. A second here, a second there, it all adds up. Now, this culture of parallelism reaches deep and wide into Maple. We're not just implementing new routines, we're fine-tuning our existing functions to make them faster. We're also making deeper changes in Maple which yield performance gains all over. So, what can you do? What can we do? We can automatically parallelize common commands. This lets people benefit from multi-core processing without even realizing it. Many commands and functions are automatically parallelized. These include matrix computation and polynomial expansion and factorization. These are automatically distributed across all of the cores of your computer. These sound quite niche, but since many operations require polynomial manipulation and matrix computation, the benefits stretch across Maple. We also have support for CUDA and local grid computing. The latter means you can easily write thread-safe code to run on your computer. The same code can then be run on a high-performance computing cluster without any changes. We also want to educate our users about the potential and the limitations of parallel computing. Thread safety may be an issue, and there are sometimes unusual floating point results when you increase the number of threads. So I wanted to introduce you to some of the team at MapleSoft who have developed our parallel computing architecture. My colleague Jason Shelby, for example, defended his PhD thesis on parallel memory management in applications that dynamically allocate memory, and his technology is now in Maple. It's a low-level feature you don't see, but it underlines our commitment to parallel computing. Darren Ohashi developed our task programming interface and co-developed the parallel memory management system. He's also our technology evangelist for parallel computing and helps our users understand the potentials and limitations of this technology through journalism and blogging. Dave Linder's expertise is in linear algebra and matrix computation, and he's passionate about performance. Frankly, he lives and breathes speed. He's responsible for integrating the latest numerical libraries into Maple, and he keeps on top of the latest developments in chip architecture and what it means for making math software faster. And finally, Paul DeMarco is an expert on distributed computing, and he's responsible for our grid computing initiative. He's also responsible for our relationship with the SharkNet project, which I'll mention later. In the last couple of years, he's also deployed Maple on a crazy computer with 16,000 nodes. So let's talk about some parts of Maple which are automatically parallelized, and some of these concepts are actually illustrated in the Maple worksheet that I'll demonstrate at the end of this webinar. So, matrix computations and linear algebra are at the core of science and engineering, and many operations can be easily parallelized. Maple automatically parallelizes several matrix operations, including matrix multiplication and inversion. For example, if I define two matrices and then multiply them together, Maple distributes the calculations across all of the physical cores of my computer. I have a laptop with two physical cores, each of which have two hyperthreads, hence the CPU utilization goes up to around 50%. And the same parallelization applies for matrix inversion and other matrix operations as well. Let's talk about polynomials. They're a fundamental building block of many computer algebra algorithms. Maple automatically parallelizes polynomial multiplication, division, factorization, and expansion. These are frequently used by higher level routines such as the GCD and factor functions, which in turn are used by even higher level routines such as normal and simplify. This means the benefits of fast multi-threaded polynomial manipulation stretches across Maple, even if you're not directly manipulating polynomials. Moving on, some very common commands are multi-threaded. For example, all Maple users, whether you're a mathematician, scientist, or an engineer, uses the concept of iterated addition, multiplication, and function mapping. These concepts have parallelized counterparts in Maple. For example, let's say that you wanted to calculate this iterated addition. On one thread, it takes about 2 seconds on my laptop. With 4 threads, it took just over a second, about 1.2 seconds to be exact. Maple automatically parallelizes the generation of Bernoulli numbers as well, and these have critical applications in topology, Taylor series, and other scientific applications as well. Let's talk about a deeper topic, and that's parallel memory management. The memory management system in Maple allocates memory for specific operations and then releases that memory for other operations. This process takes advantage of multiple cores, speeding up even serial operations. In addition, if you're running parallel code, the system takes better advantage of thread-specific memory management. This gives an overall increase in parallel performance. The garbage collector is an algorithm that handles Maple's memory usage. It allows Maple to track and reuse memory even when it's no longer in use. And to do this, the collector runs periodically and scans the memory that Maple has allocated, looking for memory that can be reclaimed. Typically, for real, non-trivial examples, it runs about 5 to 20% of the time. Previously, it was single-threaded, and this both limited the speed of single-threaded and parallel code. And we recently completed a major project in making the garbage collector run in parallel. And by doing that, your processing time is typically reduced by 5 to 10%. Your computer may have a dedicated graphics card, and they're used to accelerate CAD packages and 3D computer games. A key feature of these graphic cards is that they have many processors, often with 200 or more cores. Each core may run at a relatively low clock speed. For example, here on my computer I have a Quadro FX 58000 and it has 240 cores. Each core has a low clock speed, but they're all optimized for parallelized matrix math. Maple supports CUDA technology. This lets you offload matrix computations onto your graphics card, and it simply takes a simple software switch to do that. With this benchmark, I'm multiplying two 4000 by 4000 floating point matrices together. On my i7 quad-core laptop, this takes about 3.7 seconds, 3.8 seconds. Bear in mind that this is already split up over 4 cores. However, if I offload the calculations onto my CUDA graphics card, it only takes 1.2 seconds, and that's a real tangible time savings. I've spoken about a number of built-in parallelized commands in Maple. You can also write your own parallel programs, and there are 2 different approaches, the task model and the grid computing model. I won't go into the advantages and disadvantages of each approach in detail. They're listed on screen. But let's talk about the grid computing model. It's better suited for local and distributed grid computing. Now, with the grid computing model, you launch calculation nodes. Each node runs independently in its own memory space, but they can also send messages to each other. Maple distributes each calculation node across all of the cores of your computer. The same program can be distributed to a cluster of computers with no change in the program. Maple actually uses an implementation of the message passing interface standard distributed by the Argonne National Laboratory. And this is what a grid computing program looks like. Again, I'm not going to go through this in detail, but I've highlighted some of the language features. This approach is inherently thread safe, and the program looks like every other Maple program. It's not inherently different to what you're doing at the moment if you're using Maple. You can launch an arbitrary number of nodes, and Maple handles the task allocation. At the start of this presentation, I discussed a case study with Oxford Semiconductors. They used these programming tools, the sort of code I'm showing you now, to save time and ultimately design better products. At this point, I want to mention SharkNet, which I think is another success story for parallel computing in Maple. SharkNet is a consortium of Canadian universities who share a network of high-performance computers. Researchers and academics across Canada can log into a website and run parallel programs using one of a range of software tools, and one of these tools is Maple. The infrastructure uses Maple's grid computing functionality. Essentially, researchers write Maple programs on a local grid and then deploy them to a distributed cluster with SharkNet. And as I mentioned recently, my colleague Paul DeMarco has run Maple on a Cray supercomputer on 16,000 nodes using this infrastructure. Now let's talk about system modelling. MapleSoft also have a tool called MapleSim. It's used for multi-domain physical modelling. It's typically used by the automotive industry to model cars from the ground up, so everything from the interaction of the road with the tyres, the transmission, the powertrain, the engine, the vibration of the chassis, and perhaps even a driver model. These simulations can be complex and can take a long time to simulate or run. Often you need to repeat these simulations over and over again over many iterations of design parameters, and this can be very, very time consuming. MapleSim uses the parallel technology that we've built into Maple. This means you can now perform parameter sweeps and Monte Carlo analyses in parallel. Now, parallel computing isn't always faster. With parallel programs, you need to pass data from one process to another, and this can be slow. And the fastest known single-threaded algorithm may have fewer computations than the fastest known multi-threaded algorithm. A good example of that are FFTs. And ultimately, efficiently implemented single-threaded math routines may be faster than their parallel counterparts. Now, at this point, I just want to jump into the Maple worksheet that I demonstrated earlier, that I showed you earlier, and just show you a few parallelized routines in Maple. You can request a copy of this worksheet simply by emailing support@maplesoft.com and just ask for the worksheet that we demonstrated in the parallel computing webinar. So I spoke about parallelized matrix computation routines. As I mentioned, floating point matrix multiplication is automatically parallelized across all of the cores of your computer. Let me just zoom in. So in the first two steps of this Maple worksheet, I'm generating two 6,000 by 6,000 matrices filled with floating point random numbers. Now, if I multiply the matrices together like so and hit enter, you can see Maple is evaluating on the bottom left-hand corner, and this will take about 6 or 7 seconds. Now, when I did this, this operation was distributed across all of the cores of my computer. If I load up my Windows Task Manager, and run this operation again, you can see this this service spiking up the utilization on my quad-core laptop to around 70–80%, and then it goes down again. If Maple was just using one core, the utilization would just be around 12.5%. But since Maple distributes computations across all of the cores of my computer, you could see the utilization spiking up to a much higher level. Now, if you're trying to benchmark parallel Maple routines on your computer, this command is pretty useful. It's the usage command from the Code Tools package. Specifically, this gives you two time benchmarks. This is the real time, so this is actually how long you have to wait to get a result, and then the CPU time. This is the amount of time each CPU is active. So real time is around 6 seconds. The CPU time across the 4 cores of my computer is around 23 seconds. So you can see Maple distributed all of the calculations across the 4 cores of my computer. Now there's a number of other Maple routines which are automatically multi-threaded, such as inversion, linear system solving, and LU decomposition. Matrix computation is also multi-threaded across all of the cores of your computer. So for example, here with this command I'm artificially restricting Maple to use one CPU, one core on my computer. If I expand this polynomial, so 1 plus x plus y plus z plus d, all to the power of 22, it takes about 2.7 seconds. If I ask Maple to use 2 CPUs, this time drops down to 1.4 seconds. If I ask Maple to use 4 CPUs, the time drops down to about 1.2 seconds. Now, I'm not going to go through the other functions or routines in this Maple worksheet, but this worksheet is a good introduction to many of the routines and features in Maple which are automatically parallelized. So let's just return to this presentation. And let's talk about the future. What are we doing to better support multi-core computing and automatically parallelized math in the future? Well, the Maple kernel is the core of Maple. It's the engine that drives everything else. The kernel is primarily responsible for interpreting the Maple programming language and representing Maple data structures, and it performs basic operations on data structures and low-level math algorithms, and the kernel is written in C. We're investigating future technologies for rewriting this so that the kernel makes use of parallel computers, parallelized math. Now, that brings me to the end of this webinar. I hope I've demonstrated how Maple helps you compute faster with multi-core math routines, and I think I've demonstrated our commitment to support a greater degree of parallelism in the future.